The Canny edge detector is probably the most widely used edge detector in computer vision. It uses the best properties of the gradient operator and the Laplacian operator. So let's take a look at how the Canny detector works. First, what you do is you simply smooth the image. That's n sigma, the Gaussian right here. You convolve that with the image, you smooth the image. And then you apply the gradient operator. For instance, using the Sobel operator, which is the 3x3 gradient operator we discussed earlier. You apply the gradient operator to the smoothed image, and what that gives you are two numbers at each point, the derivative in the x direction and the y direction. And from that, you can compute, of course, the magnitude of the edge at each pixel, and you can compute the orientation of the edge at each pixel. The magnitude is what's being shown in this image here. The brighter the point here, the higher the magnitude. And now, instead of applying a Laplacian, as is usually done in the case of the Laplacian operator, two-dimensional Laplacian, what Canny does is apply a one-dimensional Laplacian. And so the one-dimensional Laplacian is applied along the direction of the edge. So we know what the direction of the edge here is. That's the vector n. So you construct a 1D Laplacian and simply apply it along that direction. So Canny's argument is that if you do this, you're not going to be affected by things that happen along the other dimension. That might end up corrupting your result here. You get a much more reliable result if you construct a 1D Laplacian operator that's been designed for that particular direction, for that particular pixel. And that's what you see here. It's a second derivative of the smooth image with respect to the direction n. And if you get a strong zero crossing there, then you declare that to be an edge, such as this one right here. So that's how you end up finding all the edges. Now, one thing that I want to discuss here, highlight, is the effect of this parameter sigma here. You can imagine that depending on how much you smooth your image, your edge results are going to change. So let's take a look at that. So here you have the image, and let's say you start off with a very small sigma here. You end up with lots of edges after applying the Canny detector. And then if you increase sigma, you see that the number of edges reduce. And if you increase sigma further, you see that you get sparser edges right here. So what's going on here is that you're exploring what's called the scale space associated with the image, and where scale represents the resolution of the image. Imagine that you had an image of a brick wall. At very high resolution, the edges would include not only the borders of the bricks, but also the fine details or the pores inside each brick. But as you pull away and you're looking at this with lower and lower resolution, you end up with perhaps none of that detail, but just the borders of the brick and so on. So when we talk about edges, they can exist at many different scales of resolution. And what Canny allows you to do, the detector, is to simply change one parameter sigma and pull out the edges in the scale that is of interest to you. And now, let's take a look at a couple of illusions associated with edges. Here is the herring illusion. It's a very interesting one. Take a look at this picture for a second, and you'll agree that the two horizontal lines that you're seeing here appear to be bowed, bulging out, right? They don't appear to be parallel, but in fact, if I remove all the other lines, you see that they are exactly parallel lines. Let's take a look at that once more. Here is the whole picture. You see two non-parallel bulging lines, and now you see that they're perfectly parallel lines. It appears that the reason this happens is that when you have acute angles in an image like this one, the human visual system tends to see these as less acute angles. And that bias that you have in the system, don't really know why that bias exists, but that bias makes you want to believe that these are actually curved lines bulging out, both of them, and not parallel lines as they actually are. Here's another really interesting illusion, very well-known illusion called the cafe wall illusion. So in this case, you see these little tiles here. And if I remove these tiles and just show you the horizontal lines, when I look at this picture right here, you see that these lines seem to be tilted with respect to each other. We can all agree on that. These horizontal lines seem to be tilted with respect to each other. If you remove the tiles, the black tiles, you see that they're perfectly parallel. Let's take a look at that one more time. Tilted horizontal lines are actually parallel lines. And in this case, it appears that the human visual system tends to see black patches as being slightly smaller than white patches. Again, we don't fully understand the reasons for this, but that bias causes these lines to appear tilted because they're holding these tiles together.